Hello there, Mr. Sutton bringing you the AB Calculus Chapter 5 Quiz 2 review answers for RAM and definite integrals. For this problem, we're trying to find the integral from 0 to 3 of this function using geometry. So I'm just going to shade in the relevant parts that I'm finding the area for under the curve that they gave us. So we've got one endpoint here at 0, another here at 3. Shading stuff in, that's going to be a triangle here and another triangle here. We just need to find these areas. So for the first triangle, we've got 1/2 base of 2 times a height of 4. And for the next triangle, we have 1/2 times a base of 1 and a height of 2. But since we're under the x-axis here, that is actually going to be negative area. So if you wanted to simplify this, that's going to be 4 minus 1, which comes out to 3. For this problem, we're trying to evaluate this integral using this graph and a little bit of geometry. So they want the integral from 0 to 3 on this one. That's going to be this area here. So it's a quarter circle, which means that we're going to have an area of negative, since it's under the x-axis, this is going to be negative 1/4 pi r squared. So 1/4 times pi times 3 squared. So this is everything that's coming together here. And if you wanted to simplify that, this is going to be, let's see, 9 pi times negative 1/4. So negative 9 pi over 4 then. For this problem, we're trying to evaluate the integral of this graph using geometry. So we're doing the integral from negative 2 to 2. So we're trying to find the area between our curve and the x-axis from negative 2 to positive 2. So this shaded area here, which is a little bit tricky. Because it's not like this is under a semicircle. It's actually this part that's not the semicircle. So we're going to have to kind of use the idea of cutting area out to get this shaded area. So there's two shapes going on here. I have this rectangle that's underneath the x-axis, so it's actually a negative area for the rectangle. And if we wanted to categorize that area, we could call that negative 4 times 2. So there's an area of negative 8 here, but we're actually losing some of that negative area to this semicircle. So if you're subtracting a negative away, you're actually adding in something. So we're going to add a semicircle, so that's going to be 1/2 pi r squared. In this case, we're adding 1/2 pi times 2 squared. So that'll offset that original negative rectangle with some non-negativeness, if that makes any sense. So if we want to simplify this a bit, we've got a negative 8. We've got a, let's see, 1/2 of 4 is 2, so 2 pi. So 2 pi minus 8 would be the simplified version of this. For this problem, we're trying to approximate the area under the function negative x over 2 plus 6 over the interval from negative 7 to negative 2 using LRAM on 5 subintervals. Since they didn't give me a table, I'm going to create one to make my life a little easier. So we've got x's and y values here. Now for the x values, we're starting at negative 7. And since I'm doing 5 subintervals to get from negative 7 to negative 2 in 5 subintervals, I'm going to go by ones. So we got negative 6, negative 5, negative 4, negative 3, and negative 2. Okay. Now since I am allowed to use a calculator on this problem, I'm going to just plug this function in my calculator and get a table here, like so. So I'm in my y equals. I'm entering in negative, let's see, alpha y equals x over 2, so fancy fraction mode here. I didn't really need to do that, but why not? All right, and I want to get a table from negative 7 to negative 2, so I'm going to do second and then window to get table set. I want my table to start at negative 7, and I want to go up by 1s each time, so let's increment that by 1s, and then do second graph to get a table out of this. And let's see here, I'd like those to actually be in decimals, so I'm going to go back and make this negative x divided by 2 instead of fancy fraction mode. And now let me try table, and there's some decimals. So we've got 9.5, 9, 8.5, 8, and 7.5, and 7. So we have 9.5, 9, 8.5, and the rest of them. Okay, so now for LRAM, I'm creating rectangles that each have a base and a height. The base on all of these is going to be 1 because it's a distance of 1 from each x value to the next x value. But the heights are going to be different. And for the first height, I'm going to take the left endpoint of the first rectangle, which goes from -7 to -6. So I'm going to be doing a base of 1 times a height of 9.5, then a base of 1 times a height of 9, base of 1 times a height of 8.5, and the same thing with 8 and 7.5. This last number doesn't end up getting used because that's the rightmost endpoint, or the rightmost y value on one of these rectangles. So that doesn't get used in LRAM. All right, let's add all these up on the calculator. And when I added these, I didn't bother multiplying them all by 1 before adding them together. You could if you wanted to, but you get 42.5 out of this. For this problem, I want to figure out an approximation for the area under -x plus 3 from -7 to 1 using MRAM over 4 subintervals. Now, it's very important to realize that they're asking for an approximation, not the true area. I could actually find the true area since this is just a line by doing some triangles and maybe some other shapes, but they don't want the true area. They want an approximation with MRAM. So let's make a table and give it to them. So if I'm doing the midpoints, and let's see, I'm going 4 subintervals from -7 to 1, that means each subinterval has a distance of 2. So let's see, the first midpoint, the first rectangle goes from -7 to -5. So the midpoint of that would be -6. And then since these are going by 2s, I would have -4, 2, -2, and 0. 0 is the midpoint of the last rectangle, which goes from, let's see, -1 to +1. There we go. All right, plugging all these in. This is going to be 6 plus 3, or 9. This next one will be 7 plus 3, or 4 plus 3 rather, which is 7. Then we've got 2 plus 3 is 5, and these are just going by 2s each time. So 3 is the last one. And now I'm just going to add them all together. So I have a base of 2 on each of these rectangles. And the nice thing about MRAM is you have the actual height here because you're not going to bother putting all the other y values in there. It's just the midpoint y values, and that's it. So we have 2 times 9 plus 2 times 7, base of 2 times a height of 5, base of 2 times a height of 3. And since these are all getting multiplied by 2s, you could get fancy and factor a 2 out of all this, and then just add all the other numbers together. So 9 plus 7 is 16, plus 5 is 21, plus 3 is 24. Multiply all that by 2, we get 48. On this problem, I'm trying to approximate the area under the f function, whose values are given in this table, using RRAM. So I'm going to be doing some rectangles here. The first rectangle, going from -3 to 1, has a base of 4, and since this is RRAM, we're going to use the rightmost endpoint of -8. So we've got 4 times -8 for the first interval, and then our next rectangle going from 1 to 8, that's a base of 7 times a height of 3. After that, we have a base of 1 times a height of 2, and after that, we have a base of 5 from 9 to 14 times the height, the rightmost height of -7. So adding all this up, we've got, let's see here, -32 plus 21, that's -11, plus 2 is -9, plus -35 is going to be -44. There we go. On this problem, we're trying to determine if approximating this integral with RRAM is going to be an underestimate or an overestimate of the true value. So first thing we're going to do is figure out if there's any critical values on the interval that we're dealing with. And we're also going to have to find the first derivative while we're at it anyway. So first derivative of -3e to the -2x, we're going to have, let's see here, -3e to the -2x times -2. So that'll be 6e to the -2x. That's our first derivative. Now, if you set this equal to 0, you'll realize there's no way to make an exponential function equal 0, so no critical values, which means that we're not changing directions anywhere between -1 and 0. So now we're just going to test a value between -1 and 0 to see if this function is increasing or decreasing on that interval. And if we test a value such as, let me see, -1/2 in here, Well, no matter what you plug into this function, it's exponential, so it's going to come out positive. So since f prime of 1/2, and I'll say negative 1/2 actually, since f prime of negative 1/2 is greater than 0, that means our function is increasing on this whole interval. So if you have an increasing function and you're R-ramming that thing, that means that you're overestimating the function, so we have an overestimate. Now, you don't actually have to explain why it's an overestimate. You just have to say increasing, therefore R-ram overestimates. So just as a little bit of a follow-up, because this is our only example like this on the review guide, if you were decreasing, R-ram would underestimate that. And for L-ram, it's exactly the opposite. Increasing functions on L-ram get underestimated. Decreasing functions on L-ram get overestimated. So when in doubt, just draw a picture of the function, increasing or decreasing, draw the type of ram, and see if you're over or under. On this problem, we're being asked to express this integral as a Riemann sum. So we're essentially trying to put it in this format. Limit as n approaches infinity of the sum from 1 to n of fxi delta x. So on all these, we're always going to start by getting the delta x, because that's going to determine what our x sub I looks like, because x sub I, we find that by using delta x. So delta x, that's going to be essentially your interval length divided by that n that's approaching infinity. That's telling you, what your change in x is going to be, because you're figuring out your total amount and you're dividing it up into an infinite number of parts. So if we use this guideline of b minus a over n, we end up with 5 minus 1 over n, or 4 over n, as our delta x. And now we're going to get the x sub I here by doing the a value, the lower limit of integration, plus I times delta x. So we've got, let's see here, an a value of 1, and I is just kind of playing itself in this motion picture, but we're multiplying that by 4 over n, so that's 4i over n plus 1. So this whole thing here, this is what you're going to apply the function in the integrand to. So we're going to be doing limit as n approaches infinity of the sum from 1 to n of, and now we're going to have all this stuff as x minus 4 times all this stuff squared, and then we're going to have this 4 over n outside here as well, and that's going to be essentially our dx there. For this problem, we're trying to convert this Riemann sum into a definite integral. So we want the format integral from a to b of f of x dx. So we need to pick out the a and the b value and also the function. And this dx is also going to be kind of important. I mean, it's going to be dx by the time you get to the integral, but knowing what the differential is in Riemann sum form is actually going to help us out quite a bit. So the dx is really kind of like a delta x, and the delta x is always this little part here on the end that has some constant over n. This constant up here, this is the interval length. This is telling us there's a distance of 5 between the a and the b value, because to get this little piece, we always do b minus a over n. And there's more. This delta x here actually gets used to form the x sub I expression that we do all the function stuff to. So if you know what this is, you can kind of pick out in here what's the a value and what's actually part of the function. So since I've got 5 over n, 5i over n, this is essentially right here I times delta x, and that means that this negative 2 must be the a value that gets added to the I delta x. So this negative 2 then is going to be my a value, and this whole thing here, 5i over n minus 2, this is all just going to kind of become x when we put it into integral form. But going a little further, while we're getting the a value, let's also get the b value. That's going to be the a value plus this 5 we were talking about here. So negative 2 plus 5 gives us 3. And now our function, since we've decided all of this stuff is going to be just one big x, since this is the a value here and it's actually part of the input, this is just going to be then 5 times x cubed minus 1. So we have integral from negative 2 to 3, 5x cubed minus 1 dx. For this problem, we're going to approximate this integral using the trapezoidal rule. So in general, that means you're going to be doing essentially base 1 plus base 2 over 2 times the height. Now, in this case, since all the trapezoids are going to be horizontal, the bases are actually going to be the y values, and the heights are actually going to be the distance between the x values, since we have sideways trapezoids. So for my first trapezoid, I've got the bases negative 3 plus negative 5 over 2 times a height of 1. Next, I've got negative 5 plus negative 3 over 2 times a height of 6 now. And then negative 3 plus negative 1 over 2 times a height of, let's see, 7 to 10, that's 3. Next, negative 1 plus negative 2 times a height of 3. And we've got a 2 down there as well. And then finally, negative 2 plus negative 1 over 2 times a height of 1. So you could actually leave it like this if it's a free response problem anyway, and it's all constant, so it counts. If you needed to simplify it, though, we'll go ahead and do that. So over here, this is going to be negative 8 over 2, so negative 4. Next, we've got, let's see, this is negative 8 over 2 again. So negative 4 times 6 is negative 24. Over here, this is negative 4 over 2, which is negative 2, times 3 is negative 6. This over here is going to be negative 1.5 times 3 is negative 4.5. And then finally, we actually have negative 1.5 over here times 1 is just negative 1.5. Adding it all together, let's see, we've got negative 28, negative 34, another negative 6 gives us negative 40. There we go. For this one, we're trying to determine if approximating this integral with the trapezoidal rule will result in an under or over estimate. Now, unlike RAM, the trapezoidal rule, you have to look at the concavity to decide if you're going over or under. So we need the second derivative of this function that we're looking at the area under. We need the first derivative first, though. So that'll be negative 4x minus 8. And then our second derivative is just negative 4. There's no critical values here, so we don't have to worry about changing concavity midstream. So then we just have to look at the direction of the concavity in this interval. It doesn't really matter what you pick in any interval, though. It's a constant value of negative 4. So our second derivative then is negative. Since that means we are concave down, a trapezoid on concave down is going to underestimate. And if you're not sure about this, you can just kind of draw a picture and then draw a little trapezoid on a concave down function. Unlike concave up, where you're overestimating it, concave down, you're going to underestimate the area under the curve. So there you are. For the rest of the problems, we're going to be using these integrals here. Integral from 1 to 3 of f, which is 5. 5 to 3 of f is 3, and 3 to 5 of g is negative 2. First thing we're going to be finding is the integral from 6 to 6 of f of x. Now, whenever you have the same lower and upper limit of integration, you essentially have an empty integral, and you have zero area out of that every single time. For this one, we're trying to find the integral from 5 to 3 of g of x dx. So that's pretty close to what we have up here. Here we have the integral from 3 to 5, and they're saying that it's negative 2. If you switch the lower and upper limits of integration, you end up kind of integrating backwards and getting negative whatever you would have gotten initially. So you just negate the value of the integral in that case. So this is going to end up being negative 2. So that's positive 2. For this problem, we want the integral from 3 to 5 of 2g of x plus 5f of x dx. So using our integral rules and properties, we're going to split this up. Since I'm adding two things together, I can split that up into two different integrals. And while I'm at it, I'm going to take out this 2 and I'm going to take out this 5 in each of those individual integrals. So my first integral, I'm going to have 2 times the integral from 3 to 5 of g of x. And for the other one, I'm going to have plus 5 times the integral from 3 to 5 of f of x dx. So converting this into actual numbers, this first one's not a problem. The integral from 3 to 5 of g of x up here they said is negative 2. So this is just 2 times negative 2. This next one, though, is a little bit of an issue. We have an integral from 5 to 3 of f of x, but not 3 to 5. So if you want to switch the limits of integration like we did here, you have to negate the area. So this is really going to be plus 5 times negative 3. But then if we have negative 4 plus negative 15, that's negative 19. For this next problem, they're having us add the integral from 1 to negative 7 of f of x with the integral from negative 7 to 3 of f of x. And initially this looks kind of weird because, I mean, why are you going from a larger number to a smaller number? But they did that up here too. We just kind of have to roll with it. The real key here is that the upper limit for one of these matches the lower limit for another one. So you could kind of think of these as being like right next to each other. In which case we just have to convert this into one big integral from 1 to 3. Do we know what the integral from 1 to 3 of f of x dx is? We do. It's up here. It's 5. So that's that problem. For this problem, we're asked for the integral from 1 to 5 of f of x dx. And if you look up here, you'll notice we don't have anything that really matches that. We have the f function. We have an integral from 1 to 3. We have an integral from 5 to 3. We don't have integrals from 1 to 5 anywhere. So I'm going to have to take these different parts here and add them together so that the lower limit of one of them is 1 and the upper limit of another of them is 5, and hopefully the other limits match. So we can do that if we write limit from, or rather integral from 1 to 3 plus the integral from 3 to 5 of f of x dx, like so. So then if I were to add these back together, I would get the integral from 1 to 5. Now this is nice as far as it goes, but let's plug in some numbers here. So this first one is given to us as 5. For this next one, we have that upside down. So if we want to make it 3 to 5 instead of 5 to 3, we have to negate that number, that area, to give us negative 3. And then 5 minus 3 is 2.